All right, so to summarize where we are, we've looked at vectors geometrically by viewing them as positional movements in space, directional movements in space, maybe another way to say it. And we've looked at the length of a single vector. We call that norm. We've also described a notion of dot product, which relates to two vectors. And we said that this relates to angle, although we've only said it, we've really not justified as to why that would be the case. Because ultimately we've just described what the dot product is computationally, algebraically, but what does it mean geometrically? Because really the topic of today's class is about norm and dot product being geometric notions of a single vector and the angle between two vectors. So, okay, let's try to make the connection between this dot product equation and angle between two vectors. So here's the thing to imagine. Imagine yourself that you have two vectors in space, wherever those two vectors are. So imagine here's vector A, and there's vector B. Now, even if those vectors are in three-dimensional space, by virtue of there being only two of them, those two vectors would lie in, at most, a plane. So if you sort of took those two vectors in three-dimensional space and you imagine the plane that contained them being, say, the xy plane, because you could sort of draw your axes in wherever you wanted them to be. If you drew your axes in such that A and B would be in a single plane, well then A and B could be drawn in the xy plane. So here's our two generic vectors, and here's our visualization of these two generic vectors in the xy plane. Now, for the purpose of getting a grip on these vectors, let's say that the vector B is B1 units right and B2 units up. So we're going B1 units along the x-axis, B2 units along the y-axis to get to the point corresponding to the end of the arrow, which is B1 units right, B2 units up, namely the vector B. And let's say the vector A also has a corresponding vector notation of A1, A2, which means A1 units to the right, A2 units up, describes the vector A. And now let's remind ourselves what we're after. We want to relate dot product to angle between the vectors. And you can see that between these two vectors, there is an angle between them. And rather than the angle, the reflex angle that's bigger than 180 degrees, let's think about the angle between them as being the smaller of the two angles, namely the angle that's going to be between 0 and 180. Okay, so here's our angle theta. We want to find a relationship between A and B and theta. And I'm going to dig deep to do this, but in order to make this happen, now you know that A and B are wherever they are, and wherever their 2 points are, you could draw another vector from the one ending point of A to the other ending point of B. Let's call this vector C for a moment. And if you had vector C, you'd have a triangle. And as soon as you have a triangle, whether it's a right triangle or not, you could apply the law of cosines. And you know what the law of cosines is. The law of cosines says that what? A squared plus B squared minus 2BC cosine of your angle is equal to C squared. Well, maybe you don't know. Actually, to be honest, I had to look this up earlier today. This is my second time going through the recording of this video because I forgot the 2 whenever I even copied it down off of what I wrote from the internet. The long story short is, here's the law of cosines, familiar from what, past mathematical experience. So, okay, fine, we're going to use the law of cosines. And in particular, let me just take a moment to encode this into our vector notation, because what was A in the law of cosines? That's the length of A. So let's refer to that as the norm of A. And B was the length of B, so let's refer to that as the norm of B, because you know that norm corresponds to length. So to write this notion of the law of cosines in our new linear algebraic notation, well, we're going to need norms to do so. And oh crap, I've already noticed an error in my formulation of law of cosines. It's not 2bc, but it's 2ab. So let me write this properly. This is norm of A. Apologies for the improper writing down of the law of cosines, but now we've got it correct, and I'm confident we're going to be sort of, in some sense, downhill from here. Now, as I write the law of cosines in our new notation, you might be saying, what the hell? That's much more cumbersome than the old way of writing it. Yes, it is more cumbersome, but it's going to be more useful to us because it's really going to be what's necessary to make the link between the two ideas. Okay, so here's something that I want to establish, because if you think about the vector c, my claim is, because the vector c goes from the end location of A to the end location of B, we can actually determine precisely what the vector c is in terms of its horizontal movement and in terms of its vertical movement. Because how far horizontally does vector c have to go? Well, vector c, to get you from vector A to vector B, would have to be b1 minus a1 units horizontally. Note, the horizontal movement of c is completely dictated by the horizontal movements of A and B, and in particular, the difference between them is going to be the length of c. And if you think, b1 minus a1, this would be some positive measure to the right, namely the positive measure to the right corresponding to the geometry of the vector c. And what about the vertical? The vertical would be a similar difference, but corresponding to the vertical components, b2 minus a2. And in this case, if you take b2 minus a2, since b2 is smaller than a2 in absolute value, and what b2 and a2 appear positive based on the picture, when you would take b2 minus a2, you would get something negative. And in fact, that corresponds as well to vector c's geometry. It's going down and to the right, so b2 minus a2 would be negative, b1 minus a1 would be positive. The story checks out here. And the long story short is, because c is a vector drawn between the end of A and the end of B, it can be described in terms of A and B. All right, we're going to use this expression of C to our advantage, because when you look at our formula, we've got A's, B's, cosine of an angle, and C. C is sort of the outlier in terms of the letters. I want C to also be in terms of A and B. And if we use this formulation for C, we can actually take this entire expression, write it in the forms of A and B. So let's take a look at this expression, and now let's get into some nit and grit. And I must say, what we're about to do is going to get really nitty and really gritty. We're only going to have to do it once. Once we get it out of the way, then we're going to see what the relation is between dot product and angle, and then we will be done at that point. But let's see what this is. So we want the norm of A squared. Now, what's the norm of A? The norm of any vector is the sum of the components squared, square rooted. So the norm of A is going to be the square root of A1 squared plus A2 squared. But we don't just want the norm of A, we want the norm of A squared. And you can see what's going to happen here, because the square root and the square are going to cancel out nicely, and you're going to end up with just A1 squared plus A2 squared. Similar for norm of B squared, because norm of B is square root B1 squared plus B2 squared, but since that is being squared, the square is going to undo the square root and give you just B1 squared plus B2 squared. Now this additional term with the A1 norm and the B1 norm, or excuse me, the A norm and the B norm, is going to be what? That's going to be square root A1 squared plus A2 squared, B1 squared plus B2 squared, times cosine theta. The issue with this term here is because neither of the square roots are being squared, and because each of the square roots involves different letters, the act of multiplying that all out is going to actually make the expression more clunky than it originally was. So for the sake of simplicity, let me just rewrite this as 2 norm of A, norm of B, cosine theta In other words, while the norm of A squared worked nicely because it got rid of the square root, the norm of B squared worked nicely because it got rid of the square root, these square roots weren't going anywhere and it was just going to get messy. So let's just keep it where it was because that was easier to look at, easier to work with, I claim, in time. So now let's look at the right-hand side because now we figured out the left-hand side and sort of simplified it as much as we can for now. Let's look at the right-hand side. The right-hand side is the norm of C squared. Now, how do you take the norm of any vector? You take its components, you square them up, you add them up, and you take the square root. So the norm of C squared is a square root squared. What is it a square root of? Well, take the first component of C, that's B1 minus A1, and square it, and then take the second component of C, that's B2 minus A2, and square it, and add them up. Note, by the way, here, so that we just see it, norm of C would be the square root of C1 squared plus C2 squared. This would be the square root of B1 minus A1 squared plus B2 minus A2 squared. So the long story short is, here is the expression for the norm of C. The norm of C just being each of the components squared, summed together with a square root. But now remember, what we've got a square root being squared, so that's going to give you just what's back inside. So B1 minus A1 squared plus B2 minus A2 squared on the right-hand side. And now that right-hand side, you see a sum squared and another sum squared. You could FOIL that out to get what the ultimate product would be. And the product over here on the left-hand side, I tell you what, let me just write it right here. That product's going to be what? B1 squared minus 2A1B1 plus A1 squared, and then plus B2 squared minus 2B2A2 plus A2 squared. The left-hand side still is what it is. We've got the left-hand side equal to the right-hand side. Now, as you look at the left-hand side and the right-hand side, I claim that we can do something to simplify here because, my gosh, we've done so much work to this point and we've got a bunch of numbers here up on the board, and let's try to make some sense of them, because if you notice, we've got an A1 squared on the right and an A1 squared on the left. So if we subtracted A1 squared from both sides, those would cancel away. We've got an A2 squared on the left and an A2 squared on the right. And so if we subtracted A2 squared, those would cancel away. We've got a B1 squared on the left and a B1 squared on the right. If we subtract those cancel away. B2 squared is also on both sides, and those cancel away. Now, unfortunately, we're not going to be able to cancel the norm of A because we don't have that on the right-hand side, or the norm of B because we don't have that on the right-hand side. The cosine also is not existing on the right-hand side. But what do we have? Let's summarize. On the left-hand side, we've got minus 2 times norm of A times norm of B times cosine theta. And on the right-hand side, we've got minus 2A1B1 minus 2B2A2. But think about this for a second. Both of those terms on the right have a minus 2. The minus 2 could be factored out. I mean, hell, let me just take a moment here because we've got B2A2 written. Let me just write that as A2B2, right? Because it doesn't matter whether you're multiplying B2 times A2 or A2 times B2. The order in which you multiply numbers doesn't matter. The order in which you multiply matrices is a different story, but we're just multiplying numbers here. These are numbers corresponding to A2 and B2 numbers along the y-axis. So whenever you look at this, note, both of these things on the left have a minus 2 in common. You could factor out. There's a minus 2 over here. So if we divide by minus 2, we'd have norm of A squared, or excuse me, not just norm of A, no squared, times norm of B times cosine theta equals A1 B1 plus A2 B2. But look at what's on the right-hand side. The right-hand side, A1 B1 plus A2 B2, is precisely the dot product of A and B. So the norm of A times the norm of B times cosine theta is equal to the dot product. And in other words, going through this process, we can see that dot product is related to the cosine between the two vectors. The cosine, I guess, in particular, of the angle between the two vectors.